This is the final go, no go poll for Flight 3 of Starship. Anybody 2?
Go.
Stage 1?
Go.
Stage 2?
Go.
Flight directors, go for launch.
Hello and welcome to the Terran Space Academy. This is Rocket Science, and today we will be working on a couple projects. The first is to help SpaceX safely bring down the International Space Station. They don't really need our help, but with a budget of $843 million, we'll do the math for just a 1% fee. That should keep the Academy going for a long time. Let's evaluate the problem. The ISS was built over several decades and has been humanity's only lasting space outpost. But in just over 5 years, we need to send it on its way to a fiery grave. I wish they would just boost it to a higher orbit and keep it for historical reasons. Can you imagine what it would be like for our grandchildren to tour this station 50 years from now? From whatever advanced spaceships they fly up there in. But that's not the current plan, so let's get busy. There is no real parallel for us to consider, but the closest is the former Soviet Union's Mir space station. Mir means peace, by the way. The Americans originally chose freedom as the name of their planned station, but once the Soviet Union fell, the US and Russia worked together to build this. The now finished structure was started in 1998 with the launch of the Zarya, or Functional Cargo Block Module. Zarya appeared to be from a previous orbital weapons system, somewhat similar to the Pallas orbital military platform. Pallas was launched with the massive Energia rocket system, but fired its engines in the wrong direction once in orbit, bringing itself down. Many suspected that the CIA had a hand in this, but it could have been just old-fashioned incompetence. Here you see what happens if you hammer your inertial guidance system in upside down. The second launch of the Energia rocket system was with the Buran shuttle. Some would say a stolen copy of the American design, but form follows function, which is dictated by physics, and most structures built for the same purpose come to look similar. The Buran had jet engines, by the way, to help itself land under power, instead of a powerless glide like the American version. The Buran flew only once before the Soviet Union collapse grounded it. The Zarya had been planned by the Soviets to contain the Skiff laser system. This had been designed in response to the American Star Wars system, a planned orbital weapons system to bring down ICBMs that was being developed during Ronald Reagan's time. Only space-based weapons could hope to do this, and laser systems work great in space. Zarya was the planned start of a Soviet orbital laser weapon system to bring down Star Wars. That, my fellow humans, is called escalation, with everyone competing to get a strategic advantage. We often bemoan what we spend on military power, until world events convince us that we didn't have enough. But in this case, after the Soviet Union's fall, Russia and America de-escalated. I was a deputy ICBM commander in Montana when this happened, and we suspected a sinister communist plot, but that wasn't the case. And the planned laser weapon became the first module of what became the ISS. The United States paid $220 million for it, but that was less than half the price of the US competition. Lockheed Martin's Bus 1. Zarya was launched by a Proton rocket, recently covered by this lesson, from the Baikonur Cosmodrome in Kazakhstan, covered in this lesson, to a 400-kilometer orbit with an inclination of 51.6 degrees. This orbit was chosen because it could be reached by all the spacefaring nations that were contributing to the ISS. The next component was brought up by an American space shuttle, with Endeavour bringing the Unity module up in 1998. Unity was made of aluminum and has 216 supply lines to carry fluids, gases, power, and data. There are several docking ports, and this is called a node. Node 1, in fact. 2 more connecting segments or nodes were built by Italy. Harmony, or Node 2, and Tranquility, Node 3. Each of these have 6 berthing ports and 8 standard payload racks, covered in this lesson. Unity can only hold 4 of these, because the Italian-built modules are bigger. All of these, including Unity, are still flying today. The ISS is divided into the Russian section, originally composed of Zarya, Zvezda, Poisk, Rosvet, Nauka, and Pikol, and the U.S. orbital segment, comprised of these 10 pressurized modules, 7 of which are habitable, with the 3 we spoke of providing connections. Some of these were built by the United States and others by our allies. The station has served for a quarter century, but in 2030, something must be done with it. China let one of their orbital habitats re-enter uncontrolled. This is not safe and could be catastrophic with something as large as the ISS. Let's look back at the largest object to undergo a controlled deorbit so far. When the Soviet Union fell apart in 1991, Mir had been flying for 5 years and was the first continuously inhabited research station in orbit. Served for a little more than 10 years with a crew of 3 usually, very similar to the current Chinese Tiangong flying now. It housed 28 Soviet and Russia-selected crews over its lifetime. The ISS can hold 7 comfortably. About 280 people from 23 nations have served on the ISS so far. By the way, one component of the Mir Station was brought up by the shuttle Atlantis in 1995. And in 1998, the Space Shuttle Discovery undocked from Mir for the last time. With the Soviet Union gone, the Russians could no longer afford to maintain Mir and planned to deorbit it in 1999. Private groups hoped to buy it, but space is expensive and no one had the funds. Deorbit was accomplished in 3 stages. The first used the thin atmosphere that still exists at these altitudes to naturally decay the orbit to about 220 kilometers. The ISS would also start to come down without frequent reboosting. The Russians sent up a Progress M uncrewed ship. The Progress spacecraft was used to resupply Mir. Ships like this are often used to boost the ISS today, but this one was carrying 2.5 times more propellant than usual. The Progress M at that time used a KTDU-80 hypergolic main engine burning UDMH and NTO. You will quite often see Soviet and now Russian ships using UDMH as a hypergolic fuel, while most American ships use MMH or monomethyl hydrazine. With a specific impulse of 305 seconds, UDMH is perfectly fine. The engine had a thrust of 3,920 newtons or 3.92 kilonewtons, and usually carried 900 kilograms of propellant on the ship. The modified one sent up to deorbit Mir would have then had about 2,250 kilograms, or 2.25 metric tons of propellant to get the job done. It would dock to Mir and be positioned to fire its engines retrograde. This can be done by docking on the forward side or prograde side, or spinning the entire station with its attitude control thrusters once you're docked. The engine burn will bring the station down to a 165 kilometer perigee. And remember that when you burn your engines on one side of an orbit, it brings you down on the opposite side of the orbit, way over here. Then you have to burn here to circularize the orbit, or come around and burn again here to lower your perigee further. The 2 burns happened at 0032 hours UTC and 0201 hours UTC on the 23rd of March 2001. The 90-minute difference shows the orbital period. The third and final burn began at 0508 hours and lasted 22 minutes. This was to make sure that the station entered the atmosphere just over Fiji, and it started breaking apart 8 minutes later, with most of it burning up over the South Pacific Ocean by 0600 hours. The South Pacific is the safest place to bring something back from orbit because it's the largest expanse of fairly uninhabited area on Earth. The same thing will need to be done to the ISS. SpaceX had been chosen for this purpose, and it will need over the next 5 years to design and build a ship capable of this maneuver. Some have suggested using Starship for this purpose. Let's look at this option first. The ISS has a mass of about 450 metric tons. A Starship sent up would itself have a dry mass of at least 125 metric tons. I know the goal is 120, but I'm not convinced they'll get there in 5 years. The total for the Starship alone is about the same as the Mir Station, which was 130 metric tons, not counting the propellant that will be in the Starship. Normally, Starship will be left in orbit with just enough propellant to deorbit itself and land. Sending it up with more propellant requires it to burn more propellant. But they haven't been launching these fully fueled since Flight 1, and right now the Starship can lift about 50 metric tons of payload to low Earth orbit. We'll replace that payload mass with extra propellant, and there should be no problem. The Starship will dock with the ISS with a nose-mounted docking system for this purpose, either on the prograde side of the station, or if a docking point is not available there, after the station has swung around. There's no reason to attach and then spin. The total mass once docked would be 450 plus 125 plus 50, so 625 metric tons. This massive object must be deorbited very precisely. At a combined mass of 4 times Mir, an engine explosion at the wrong time could bring all of this down on a major city. The risk is small, but ignoring small risks is how we lose people in space. If we start the first burn at apogee, at the highest point of the orbit, we will bring the lowest point, the perigee, even lower. The apogee of the ISS is 422 kilometers and the perigee about 413 kilometers. Let's bring that orbit down to 150 kilometers. That's where we saw the Starship on its last flight start to heat up and produce plasma, so we know there's air up there. The ISS is orbiting at about 7.67 kilometers per second. And if we lower the orbit to 150 kilometers, that would be 7.82 kilometers per second, a difference of 150 meters per second. That doesn't seem like much, but remember this is low Earth orbit. If we were coming back from geosynchronous orbit, it would be a very different story. I like to manually put these equations into a spreadsheet, run all the numbers, find an online calculator, and then double check, and wait for you guys to find my errors. Let's get started. If we have an initial mass of 625,000 kilograms, a burn producing that delta V would take us down to just over 600 metric tons. So we would burn 25 metric tons. How long would it take? Well, acceleration equals the change in velocity over the change in time. So the change in time will equal the delta V over the acceleration. If we limit our acceleration to just over 2 Gs, let's say 20 meters per second squared, I think the station could handle that, and do the math, we get 7.5 seconds. Can we burn 25 tons of propellant in 7.5 seconds? To know this, we need to know our mass propellant flow. To know our mass propellant flow, we need to know the force required. To produce this acceleration on a mass of 625 metric tons, it would take an initial force of 625,000 kilograms times 20 meters per second squared, so 12.5 meganewtons. To calculate the mass propellant flow from force, we will need to know the exhaust velocity. If we use the 380-second specific impulse of a vacuum Raptor and multiply by the force of gravity on Earth from our equation here, we get an exhaust velocity of 3,782 meters per second. Now that we know the force and exhaust velocity, we can calculate the mass propellant flow by using the equation F equals m dot times VE. Remember both of these equations. That means the mass propellant flow, m dot, would equal force over exhaust velocity, and they'll be burning a little more than 3,350 kilograms of propellant per second. If we burn at continuous power, we would indeed burn our 25 metric tons in 7.5 seconds. But at engine shutdown, what would our acceleration be? We can't forget that as we're using our engines, we're losing mass. And we don't want our g-forces to get too high. If we apply this force to the final mass, we see that we get 20.82 meters per second squared, so 2.12 G. No problem. But is there another option? If we know the delta V that it takes to bring down the ISS, how can we calculate the amount of propellant it will take if we use some other type of vehicle and we don't know our starting mass? By using this equation. This is the basic rocket equation modified to calculate the initial mass. If we know the final mass and delta V needed, the final mass of the ISS will be 450 metric tons or 450,000 kilograms. The delta V we calculated needing was 150 meters per second. And using these numbers, we get an initial mass of 468,477 kilograms. So we would need 18,477 kilograms of propellant, not counting the mass of our deorbit vehicle, which changes things because we're also decelerating it. Could we just attach an empty Dragon crew capsule and use its Super Draco engines to bring down the ISS? The Crew Dragon itself has a propellant mass of 2,562 kilograms, with 18 Draco engines for attitude control and orbital maneuvering, plus those 8 Super Dracos on the Crew Dragon, described in this lesson. These are only used for in-flight emergencies, so they should be available to us in orbit, and they use the hypergolic propellants MMH and NTO, or monomethylhydrazine and nitrogen tetroxide, with a specific impulse of about 300 seconds in vacuum. The Crew Dragon mass is about 7,700 kilograms at re-entry, but that can include 2,507 kilograms of return cargo. Let's say a stripped-down mass would be 5,000 kilograms, or 5 metric tons for the dry mass. So if we use the combination of those for our final mass for the ISS, that would be 455 metric tons of deorbited mass. And using our new specific impulse of 300 seconds, we multiply that by 1g and get 2,943 meters per second exhaust velocity. We put that into our equation and we get 478,792 kilograms of initial mass. That means we need about 23,800 kilograms of propellant. The Crew Dragon only has, even stripped down, 10 cubic meters of volume. The density of nitrogen tetroxide is about 1,500 kilograms per cubic meter, and MMH is 875 kilograms per cubic meter. If the entire volume of the Dragon became a propellant tank, it couldn't hold more than 15 metric tons of the densest propellant, NTO, which isn't much good without the MMH. And the oxidizer to fuel ratio of these engines is about 2.15 to 1, so 2.15 kilograms of NTO for every 1 of MMH. So the overall propellant mass would be less because we need room for the less dense MMH. Plus, Falcon 9 can only lift about 22.8 metric tons to low Earth orbit expendable, and we needed 23.8 metric tons. So let's do something different. We'll use a SpaceX Falcon Heavy instead. The Falcon Heavy is 70 meters tall and has a launch mass of 1,420 metric tons. It would cost us about $150 million in fully expendable mode. We'll bump that up to $200 million for the modifications we're going to make, leaving us with a nice profit. It can launch 63.8 metric tons into low Earth orbit and is comprised of a central core and 2 boosters, each of which has a height of 41.2 meters and an empty mass of 25.6 metric tons, and a propellant mass of almost 396 metric tons. The second stage has an empty mass of 3.9 metric tons and a propellant mass of almost 93 metric tons. Let's do this. Let's use a strengthened stripped-down Dragon capsule and a modified second stage as a propulsion module. We'll need to shorten and strengthen the trunk or just get rid of it. Our new propulsion stage will be 1/3 the length of a normal Falcon second stage. The standard Falcon 9 second stage is 13.8 meters tall, so let's try 4.5 meters first. The second stage has 1 Merlin vacuum engine with a mass of 550 kilograms. Let's subtract that from our normal dry mass, leaving us with about 3.35 metric tons, and take 1/3 of that, so a little less than 1.12 metric tons. Add that back to our Merlin vacuum mass, and we get a new dry mass of 1.67 metric tons. This should be able to hold 31 metric tons of propellant, since the full second stage can hold 93, and this is 1/3 that size. That gives us a mass of 32.67 plus at least 5 for the Dragon capsule. We need that to dock, giving us a total of 37.67, and we'll round that to 40 metric tons total. Our Falcon Heavy can lift this with tons to spare. So now we have a Falcon Heavy with an extra modified second stage as a propulsion element, which is holding at least 31 metric tons of propellant. Will this bring down the ISS? Well, the ISS has a mass of 450 metric tons, and we attach our 40 metric ton Deorbit Dragon for a total of 490 metric tons. We'll estimate our burnout mass at 460 metric tons, leaving a little reserve. Can we deorbit the ISS? The Merlin vacuum engine is burning RP1 and liquid oxygen. It has a specific impulse of 348 seconds in vacuum. If we look here, we see that if we know the initial mass and an estimated final mass, we can calculate the delta V using the basic rocket equation, and we see that we have a lot of delta V to spare. As an exercise, if we run that for other propellants, like the less efficient hypergolic MMH and NTO, or the more efficient methane and liquid oxygen, we get these results. And we see that we could use our propulsion module with hypergolic or methane and easily get the job done. The problem is, what engines do you have available, and how much will the volume change based on the density of these propellants, affecting your dry mass and changing everything else? The easiest thing to do is use the standard Merlin engines as we've described. We could do this without the Dragon capsule, but I would like to have the Super Dracos available in case something goes wrong. And I personally would install explosive charges at every node point prior to the deorbit attempt. If anything went wrong, I'd wait until the station started to re-enter the atmosphere, wherever it was, and blow it up. Some small steel pieces might survive and go through someone's house, but it's unlikely much aluminum would survive the re-entry. Now let's look at last week's assignment. If we were to take 100 Raptor 2 rocket engines with a specific impulse of 330 seconds and put them around this truncated Aerospike base and on our single stage to orbit ship, the specific impulse will improve, since Aerospikes have maximum efficiency at all altitudes, including in vacuum. Each of these Raptors has a maximum thrust of 230 metric tons, so 100 of them could negate or hover over 23,000 metric tons of mass. At a thrust-to-weight ratio of 1.5, they could lift over 15,000 metric tons, 3 times the mass of the current Starship. But we could have figured that out by dividing the 100 by 33, the number of Raptors on a Super Heavy booster right now. With an initial mass of 15,000 metric tons and assuming an average specific impulse of 375 seconds, we would have a final mass of 1,165 metric tons. But what was our dry mass? Let's use the same ratio as that of the Super Heavy booster. It has a dry mass of about 250 metric tons right now, but they want to get it down to 180. Using the 250 and dividing by its current launch mass of 3,580 metric tons, we get 7%. Let's multiply our initial mass by 7% and get 1,047 metric tons. Subtracting that from our final mass, we get a payload mass of 118 metric tons. Now this ship would need to have some restartable engines to come back and land, but that's not too much of a complication. The Chrysler SERV was going to use jet engines, but their mass is much higher than that of a much more powerful rocket engine. The only difference is you have to carry your oxidizer with you. Let me know if you come up with anything different for any of these numbers. I do this because I love the science of spaceflight and hope to see humanity move into the solar system in my lifetime. Fans of this channel have gone from interested college students to accomplished aerospace engineers. I appreciate every subscriber, and especially those who support us on Patreon. Thanks for listening, and stay safe. At Astra Pro Terra.